In the wide, patient work of sky surveys, the first encounter with a new object begins as a faint point that refuses to stay still. A field of stars holds its pattern from one night to the next, but a small body closer to the sun shifts slightly against that fixed backdrop. The discovery circumstances unfold in layers that start with the largest setting. A telescope watches a planned region of the sky, returning images at regular intervals, and software compares those images to find anything that changes. Most changes are familiar and are quickly filtered away. Some are artifacts from the detector. Some are cosmic rays striking the sensor. Some are satellites that leave brief streaks, and some are known asteroids whose paths are already catalogued. The remaining candidates are checked again because a discovery claim begins with repetition. A genuine moving object shows a consistent displacement that matches the time gap between exposures, and it appears as a point or a small blur whose shape fits the optics and the atmosphere at that moment. When the candidate persists across several images, it earns a deeper look. The initial measurements are built from astrometry, the practice of mapping positions on the sky with reference to known stars. Each image contains many stars whose catalogued coordinates are already established. The telescope image is not a perfect grid, so the transformation between pixel coordinates and sky coordinates must be solved each night. Small distortions from the optics, the temperature of the instrument, and the way the detector is mounted all bend the mapping slightly. The solution uses many stars in the field spreading across the frame so that distortions can be modeled. Once the mapping is computed, the moving object's pixel position becomes a right ascension and a declination tied to an exact timestamp. That timestamp matters as much as the position because the object is not simply located, it is located at a moment. Even a timing offset of a small fraction of a second can shift a fast mover enough to matter when the object is nearby. The designation assigned at discovery is a label for a workflow rather than a story. A provisional name like 3i Atlas or a similar survey tag indicates the reporting pipeline and the fact that the orbit is not yet fully secured. At first, the object is only a series of points, with times attached a thin trail of evidence across the celestial sphere. The earliest reports are sent quickly to central clearinghouses, where other observers can verify the detection. Verification does not mean trust alone. It means independent images taken with different instruments under different skies that find the same moving point where the first measurements predict it should be. If another telescope finds it, the object becomes real in the shared network of observers, and the measurement arc begins to lengthen. At this stage, the object's brightness is one of the first practical constraints. Brightness determines how easily it can be followed, and it hints at a few physical possibilities without proving any of them. Brightness may come from reflected sunlight off a solid surface, or from sunlight scattered by dust and gas if the object is active. Early images can look like a clean point or show a slight fuzziness. Fuzziness is not always activity. It can also be poor seeing focus drift or trailing if the exposure is long and the object moves during the exposure. Observers examine the shape of the light distribution and compare it to nearby stars in the same image. If the candidate looks wider than the stars in a consistent way, and that difference persists, across nights it raises the possibility of a coma, a cloud of gas and dust around a nucleus. If it matches the stars, it suggests a bare or quiet body, at least at the sensitivity of those images. The first orbital estimate is not yet the story of an altered trajectory. It is the story of turning a handful of measurements into a preliminary path that allows the object to be recovered. Recovery is the key word because without it, the object can be lost among the stars. A small body can fade quickly as geometry changes, and a weak initial orbit can point observers to the wrong patch of sky. Early orbit determination often uses methods that assume a gravitational path and solve for the best set of orbital elements that match the measurements. With a short arc, many solutions fit nearly equally well, and the uncertainty region on the sky can be large. Even then, a preliminary orbit can provide a prediction for the next night that is good enough to try. When the object is found again, the uncertainty shrinks. Each new observation anchors the trajectory more firmly, reducing the space of plausible paths. The discovery circumstances also include the practical limits that shape what is measured. The atmosphere bends and blurs light, and its effects are not constant. Temperature gradients can shift images slightly. Wind can shake a telescope. The brightness of the moon can wash out faint objects. The object may be visible only in a short window before dawn or after dusk. In those windows, the telescope is looking through more air, which increases refraction and scattering. Refraction moves the apparent position of an object, and the correction depends on the object's altitude above the horizon as well as local conditions. Modern pipelines correct for refraction, but the correction is only as good as the inputs. This is why a discovery is not a single measurement, but a chain of measurements across different conditions so that a consistent path can emerge from the noise. As the first days pass, the network response widens. Observatories with larger mirrors can detect the object at fainter magnitudes, extending its track. Different filters can reveal color, and rough color can hint at surface composition or dust properties, though only cautiously. If a spectrum is attempted, it may show gas emission lines, or it may show only a reflected sunlight continuum. In the earliest phase, spectra are often noisy, and the main goal is still positional: keep the object found, keep the arc growing, keep the timing precise. With each report, the orbit is updated and predictions improve. A few days can transform a fragile orbit into a stable one. A few weeks can turn an uncertain curve into a well-determined trajectory. The claim that a trajectory has altered is not yet in the evidence at this outermost stage, but the seeds of that later claim are already present in how the measurements are made. The discovery pipeline assumes certain models, relies on certain star catalogs, and filters out patterns that do not look like genuine motion. A moving object is identified by the regularity of its shift between images, but real objects can behave in ways that complicate that regularity. If the object is active, jets can change its brightness over hours, affecting how its center is measured. If it is very close, its apparent motion can be rapid and curved over a single night. If it is faint and near the detection limit, noise can pull its measured position by small amounts. The initial circumstance is therefore both decisive and delicate. It is decisive because it establishes the object as something that exists and can be tracked. It is delicate because the earliest points will remain part of the orbit fit, and any small bias in them can echo forward into later interpretations. The outer setting remains simple: a dark sky, a telescope a pattern of stars, and a faint moving point. The work in this region is to secure the reality of the object and to build a trustworthy record of where it is and when. Before any discussion of puzzling behavior, the discovery stage demands discipline. It demands repeated measurements, careful calibration, and a willingness to treat the first orbit as provisional. In that calm and procedural beginning, the object's path is not yet a mystery. It is a developing line drawn by patient observation, becoming clearer as the nights accumulate. The moving point on the detector becomes a trajectory only after its apparent motion is translated into geometry. The sky presents positions as angles, not distances. Right ascension and declination describe where something lies on the celestial sphere, like latitude and longitude projected onto a dome. Over minutes and hours, the object shifts against the star field, and that shift is the first visible trace of motion. Yet the same apparent shift can come from very different real paths, depending on distance, viewing angle, and the motion of the observer. The observer is not stationary. Earth rotates, carrying the telescope in a circle each day. Earth also travels around the sun, changing the line of sight over days and weeks. A measured position is therefore a vector from a moving platform toward a target, and orbit building is the process of inferring the target's motion in space from a sequence of these time-tagged vectors. The geometry begins with the simplest conversion. Each astrometric measurement provides a direction in space at an exact time. If the direction is written as a unit vector, it points from Earth toward the object. With several such directions on different times, the object must lie somewhere along each line, but the distance along the line is unknown. The problem is under-constrained at first. This is why early orbit methods often use assumptions about gravitational motion and solve for a path that makes those directions consistent with a Keplerian orbit, the idealized path under a central gravitational force. In practice, the orbit is a best match because no measurement is perfect, and the real solar system includes many small perturbations. The aim is not to find a single exact curve, but to find the curve that minimizes the differences between predicted and observed directions weighted by estimated measurement errors. Apparent motion on the sky has a speed and a curvature. Over short times, the object may appear to move in a nearly straight line, and its angular speed can be measured in arcseconds per hour or similar units in technical work. In this script, those units are kept as plain words, and the concept remains central. A fast angular motion often means the object is nearby, while a slow angular motion can mean the object is distant, though the relationship is not unique. A nearby object can move quickly because parallax is large. Parallax is the apparent shift in position of a nearby object when viewed from different locations. Even as Earth rotates, the telescope's location changes by thousands of kilometers relative to Earth's center, and this can produce a measurable parallax for close objects. Over a single night, parallax can bend the apparent track slightly. When the object is farther away, parallax from Earth's rotation is smaller, and the track is more nearly a simple drift against the stars. The conversion from angles to a real trajectory also depends on the reference frame. Measurements are taken from a location on Earth's surface, but orbit calculations are usually done from a frame centered on Earth's center or on the solar system barycenter, a point near the center of mass of the solar system. The reason is practical. A surface location is subject to Earth's rotation and small wobbles, while the barycentric frame allows cleaner integration of gravitational forces from the Sun and planets. To move between frames, the observer's exact position must be known. That includes Earth's shape, the observatory's latitude, longitude, and altitude, and the timing standard. Timing standards are not a detail. A timestamp tied to a precise scale, such as coordinated time, allows the conversion from a surface measurement to an Earth-centered line of sight that accounts for Earth's rotation at that moment. If the timestamp drifts, the line of sight rotates slightly, and that rotation translates into an apparent position error. A second geometric layer comes from light travel time. Light does not arrive instantly. If an object is far away, the light measured at the telescope left the object earlier. In orbit fitting, this means the object's position at the emission time must be consistent with the observation time. The correction is small for nearby objects and grows for distant ones. For a small body within the solar system, the correction is typically manageable, but still included in high-precision work. It matters most when trying to detect subtle non-gravitational accelerations later, because those accelerations can be of the same scale as the smallest systematic errors. The geometry also includes aberration, the apparent shift in direction due to the motion of the observer, similar in concept to how rain appears to slant toward a moving vehicle. Earth's velocity around the Sun changes the apparent direction of incoming light by a small angle, and this is corrected with well-established formulas. Even after these corrections, the measurements are still a series of angles. The leap toward a trajectory depends on how those angles evolve with time. A purely gravitational orbit produces a predictable pattern. Near opposition, when the object is roughly opposite the Sun. In Earth's sky, apparent motion can be dominated by Earth's own motion, creating retrograde loops for some objects. Near conjunction, when the object is near the Sun in the sky, observations become difficult, and the apparent motion can be small and uncertain. If the object is on a highly elongated path, the apparent motion can accelerate as it approaches perihelion, the closest point to the Sun, and slow as it recedes. Each of these patterns is familiar in orbital mechanics, but the fit depends on the quality and spacing of the data. Uncertainty enters the geometry at every step. Each measurement has an error ellipse a region on the sky where the true position is likely to lie. The size of that region depends on signal to noise, the sharpness of the image, the stability of the reference star positions, and the precision of the mapping from pixels to sky coordinates. When multiple measurements are combined, their errors do not simply average away. Some errors are random and shrink with many points. Others are systematic and can persist, such as a bias in a star catalog in a particular region of the sky, or a slight timing offset in an instrument. Orbit-fitting methods attempt to estimate these uncertainties and to adjust weights accordingly, but the process is never perfectly automatic. Skilled analysts look for patterns in residuals, the differences between observed positions and predicted positions, because patterns can reveal systematic errors or real forces. The phrase "altered trajectory" begins to acquire meaning here, but cautiously. A trajectory can appear to change simply because the earlier geometric conversion assumed the wrong distance. As new data arrive from new viewing angles, parallax becomes clearer, and distance estimates shift. When distance shifts, the inferred orbit shifts, and the predicted future positions shift. This can look like a change in trajectory, but it is a change in knowledge rather than a change in the object's path. A true physical alteration would mean that even after the orbit is well determined, the object departs from the predicted gravitational path in a way that cannot be explained by measurement error or by the standard corrections. This is not decided at discovery. It is decided after geometry is tested across time and across observing stations after the object has been followed through enough of its path that the remaining uncertainty is small compared to the claimed deviation. The outer geometric work continues as the arc lengthens. Observations from observatories at different longitudes can add parallax through Earth's size. Observations from different hemispheres can reduce geometric degeneracies. As the object moves along its apparent track, it samples different star fields, and this reduces the risk that a single region of catalog bias drives the result. Each new set of angles tied to accurate time becomes another constraint on the space curve that the object must follow. In this steady accumulation, the sky geometry shifts from a simple motion against stars into a structured inference problem, where every correction is known, every assumption is noted, and the remaining differences are tracked. Only after this careful translation from apparent motion to real trajectory can any later claim about unexplained behavior be measured against something solid. With a growing set of time-tagged sky positions, the next outer layer is the initial orbit fit the step, where scattered points are turned into a coherent path that can be projected forward. The phrase best fit sounds simple, but it carries a disciplined meaning. It does not claim the orbit is true in an absolute sense. It claims that among the family of possible orbits consistent with the physics assumed in the model, one set of parameters produces the smallest overall mismatch between what is observed and what the model predicts, given the estimated errors of the observations. In practice, the model at this stage is usually gravity-dominated with the Sun as the primary attractor and the planets as additional perturbing masses. The measurements are lines of sight from a moving Earth, and the unknowns include the object's position and velocity at a chosen reference time. From those unknowns, the orbit can be expressed in familiar elements that describe its size, shape, and orientation. The important point in this region is that the elements are not a direct measurement. They are a compact description of the state that best accounts for the observations so far. The first orbit fit begins under constraint, because a short observation arc cannot uniquely determine distance. 2 nights of data can show motion, but many 3-dimensional paths can produce the same angular drift. Even with 3 nights, the problem may remain weak if the viewing geometry does not change much. The orbit fitting process therefore leans on the structure of gravitational motion. A body under the Sun's gravity follows a conic section, and for most small bodies, the path is an ellipse or a very long ellipse that appears almost parabolic over a limited arc. The fitting algorithm searches for the parameters that make the predicted sky positions match the measured ones. It does so by iterating because the relationship between orbital parameters and observed angles is nonlinear. A small change in distance can produce a large change in predicted parallax. A small change in velocity can change where the object will be by the next night. The algorithm adjusts parameters, computes predicted positions, compares them to observations, and adjusts again until the remaining differences are minimized in a defined way. Those remaining differences are the residuals, and they become the language of uncertainty. A good fit does not mean residuals vanish. It means residuals are consistent with the expected measurement noise and do not show a systematic pattern. Each observation is weighted. A high-quality astrometric point from a stable instrument under good seeing is given more influence than a marginal point near the detection limit or taken through thick atmosphere. Weighting is not a moral judgment. It is a practical way to avoid letting low-quality data pull the solution away from what the best data indicate. Yet even the best data can carry hidden biases, and this is why orbit determination is never only a numerical exercise. It is a continuous audit of inputs, assumptions, and outputs. Uncertainty is described with more than one number. The fitted orbit has a covariance, a mathematical object, that encodes how uncertain each parameter is and how uncertainties in different parameters are linked. Distance and velocity, for example, can trade off in early solutions. A slightly larger distance can be compensated by a slightly different velocity to keep the predicted angles similar over a short arc. This produces elongated uncertainty regions in parameter space. When that covariance is propagated forward in time, it becomes an uncertainty region on the sky where the object is expected to be on a future date. Observers use that region to plan recoveries. If the region is wide, a recovery can fail, even if the object is present, simply because the search area is too large for available telescope time or the object is too faint. This is why early orbit fitting is focused on practical predictability rather than final precision. The task is to keep the object in hand night after night until the uncertainty collapses. A key distinction emerges here between uncertainty and error. Uncertainty is the stated range in which the true value may lie based on known noise sources and model assumptions. Error is the difference between a reported value and the true value, which is usually unknown. A fit can report small uncertainties and still be wrong if it underestimates a systematic bias. This can happen if timing is slightly off, if the star catalog used for reference has a local distortion, or if the object's measured center is shifted by an asymmetric light distribution. In early stages, especially for faint objects, the centroid of the light can be pulled by noise. If the object has a weak tail or coma, the brightest pixel region may not coincide with the nucleus. Measuring the center then becomes sensitive to the chosen algorithm and to the seeing. Small biases of this kind can align over multiple images from the same instrument, producing residuals that look smaller than they should because the errors are correlated. Correlated errors are dangerous because they mimic precision. They can tighten the fit while shifting it. The orbit fit also depends on the time span of the observations, not just the number of points. Many points taken in a single night provide a good measure of instantaneous angular motion, but they do not greatly improve knowledge of curvature over days. Curvature is what reveals acceleration and therefore distance and orbital shape. As the arc lengthens over nights and weeks, the object's path across the sky begins to curve in a way that cannot be matched by the wrong family of orbits. Parallax changes as Earth moves, and this change provides a baseline that breaks degeneracies. The orbit solution then becomes less a flexible guess and more a constrained description. The uncertainty shrinks not smoothly, but in steps as new geometry enters the data set. A well-placed observation at a time of rapid geometric change can reduce uncertainty far more than many observations taken under nearly identical conditions. During the initial fit, analysts often compute alternative solutions that are still consistent with the data within uncertainties. This is not indecision. It is an honest mapping of what the data allow. In this phase, a single headline statement like "physics cannot explain" it is not part of the work. The work is to determine whether the orbit is truly unusual or whether it only appears unusual because the solution is not yet secure. A change between successive orbit updates is expected. The first fit may imply a certain perihelion distance, then a later fit shifts it. The first fit may suggest a long period, then the period changes. None of these are evidence of a physical alteration. They are evidence of uncertainty becoming smaller. A genuine physical alteration would appear as persistent residuals that remain after the orbit is well constrained and after known systematic sources are ruled out. At this stage, the orbit fit is still building the foundation needed to ask that later question. The handling of uncertainty also includes outlier rejection, a careful practice that must be restrained. Sometimes a measurement is plainly inconsistent, perhaps because a faint background star overlaps the object biasing the centroid, or because a tracking glitch smears the image. Excluding such points can improve the fit, but exclusion can also hide a real effect if applied carelessly. The discipline is to examine why a point is an outlier. If the reason is instrumental or environmental exclusion is justified. If the reason is unknown, exclusion is provisional, and the uncertainty budget should reflect that. In a healthy analysis, a point is not discarded simply because it disagrees. It is investigated. The aim is not to force agreement, but to understand disagreement. As the initial orbit fit stabilizes, the language used becomes more precise. Instead of saying the object changed course, analysts might say the orbit solution updated as additional astrometry extended the arc. Instead of saying the motion is impossible, they might say that a purely gravitational model leaves systematic residuals at a certain level. Those residuals are the bridge to later inner regions, but they are not yet a mystery by themselves. They are the measured gap between model and data with uncertainty bars attached, and with a record of how that gap behaves as more data arrive. The foundation is built in this region by insisting that every claimed deviation be measured against a fit that has earned trust through time-span, cross-observatory confirmation, and careful accounting of error sources. Only then does it become meaningful to ask whether the object's trajectory is behaving in a way that exceeds what the gravitational baseline and measurement uncertainties can explain. Once the object is no longer a brief appearance but a persistent target, the work shifts to refined tracking, where the observation arc becomes long enough to tighten the orbit in a physically meaningful way. The arc is not simply the time span between first and last measurements. It is also the diversity of viewing geometry contained within that span. As Earth continues along its orbit, the direction from Earth to the object changes. The object itself moves along its path, altering its distance phase angle and apparent speed. Each of these changes provides leverage. The refined stage is where a trajectory begins to behave like a testable prediction. The orbit solution does not merely accommodate the data already taken. It successfully forecasts where the object will be seen next with a narrow uncertainty region that observers can rely on. Tracking improvements begin with better astrometry. Early detections may be near the survey's sensitivity limit, leading to noisy centroid measurements. As follow-up telescopes target the object deliberately, exposures can be tailored. If the object is faint, observers can stack multiple short images aligned on the object's motion to increase signal without smearing. If the object is moving quickly, exposures can be shortened, or the telescope can track at the object's rate, producing a sharper image of the object while stars trail. Each choice changes the measurement approach. When stars trail, the reference frame must be handled differently, and this can introduce its own uncertainties. When the object is allowed to trail while stars remain points, the object's position must be defined in a consistent way along the trail. In either case, refined work aims to produce astrometric points with known stable error properties. A longer arc also invites the use of multiple observatories with different systematics. This diversity is not incidental. It is a safeguard. If all data come from one instrument, correlated biases can remain hidden. When the same motion is measured by independent systems, agreement becomes more trustworthy. Observations from different latitudes and longitudes provide parallax and reduce degeneracies in distance. Observations taken in different filters can test whether the object's measured center shifts with wavelength, which could indicate coma asymmetry or dust effects. If an object's light distribution changes over time, the measured centroid can drift, even if the nucleus follows a predictable path. Tracking programs therefore monitor not only position, but also morphology and brightness, because these provide clues to whether the astrometry traces the nucleus or a changing cloud around it. As the arc lengthens, the orbit fit transitions from a regime of many plausible solutions to a narrower family. This transition is visible in the predicted positions. Early on, predictions can diverge quickly over days. Later predictions remain close even when the data are extended by a night or two. The residuals become more informative as well. When uncertainty is large, residual patterns can be absorbed by slight shifts in orbital parameters. When uncertainty shrinks, the same residuals can no longer be explained away by parameter adjustments without ruining the fit elsewhere. This is why persistent residuals that grow with time are taken seriously. They may indicate that the model is missing a force, or that a subtle systematic error remains unaccounted for, or that the object's measured center is being biased by physical changes in the object's appearance. The refined stage also improves timing and calibration. High-precision work checks the time standard at the observatory, ensuring that recorded exposure times are correctly synchronized. It verifies the shutter timing and the actual midpoint of exposure, because a camera's reported start and end times may not fully reflect how light accumulates. It checks the star catalog and may apply corrections if known catalog biases are present. Modern astrometry relies heavily on reference catalogs that provide star positions and proper motions, the slow drift of stars across the sky over years. If a catalog's proper motions are slightly wrong for some stars, the reference frame can shift. In the refined phase, analysts may restrict reference stars to those with well-determined motions and may test the solution with different subsets of stars, to see if results change. Stability under such tests increases confidence that the orbit is real and not an artifact of the reference grid. A longer arc allows the orbit to be integrated with more complete gravitational models as well. While early fits may approximate planetary perturbations, later fits often include precise ephemerids for planets and may include relativistic corrections that slightly adjust the path of light and the motion under gravity near the Sun. For most small bodies, these corrections are small, but in a situation where claims of unexplained deviations appear, small corrections matter. They matter because the magnitude of many non-gravitational accelerations is small, and the line between a real anomaly and a modeling omission can be narrow. The refined phase is therefore a phase of model completeness. Analysts ensure that the baseline gravitational model is as accurate as practical before attributing residuals to new physics or unusual forces. Within this growing precision, the language of trajectory alteration becomes more concrete. A trajectory in this context is not a visible line in space. It is the set of predicted positions at future times given an assumed model. If repeated observations find the object consistently offset from those predictions in a systematic way, the prediction is wrong. The next question is why. In many cases, the answer is simply that the model must include a non-gravitational term, such as a small acceleration that depends on distance to the Sun. For comets, this term is often associated with outgassing, where sunlight warms the nucleus and volatile ices sublimate into gas, carrying dust and creating jets that act like weak thrusters. For asteroids, subtle thermal effects can matter. But before any of that, the refined tracking phase must confirm that the offsets are real and not produced by shifting measurement quality. One important refinement is the use of astrometric debiasing. Even the best catalogs can have regional distortions, and surveys can have known patterns of small offsets. Debiasing applies statistical corrections derived from comparisons between observed and expected positions of many objects. If a survey is known to measure positions slightly eastward in a certain declination band, that bias can be corrected. Such corrections must be used carefully because they are not specific to the object. They are population-level adjustments that assume the bias is stable. In refined tracking, applying or not applying such corrections can change the residual pattern. Analysts test both. If a claimed anomaly disappears when known debiasing is applied, the anomaly likely belonged to the measurement chain. If it persists, it becomes more interesting, though still not decisive. The refined phase also involves photometric monitoring. Brightness changes can indicate rotation activity or changing viewing geometry. A rotating, elongated object can brighten and dim periodically as different cross-sections face the observer. If the rotation state changes, perhaps due to jets or thermal torques, the brightness pattern can change. This matters because a changing rotation can change how non-gravitational forces act. It can also change the location of the brightest region in a coma biasing astrometry. Observers therefore correlate positional residuals with brightness and morphology. If residuals increase when the coma brightens, the measured center may be shifting due to activity. If residuals show no relation to brightness, the cause may lie elsewhere. As weeks turn into months, the orbit becomes a shared product of many observers, and the uncertainty can shrink to a level where small accelerations become detectable. At that point, the object's track is no longer a rough line. It is a carefully stitched record with known timing, known reference frames, and a gravitational model that has been checked. This refined stage is the necessary outer foundation for any later claim that physics cannot explain the motion. Without it, the claim would rest on moving sands. With it, the claim becomes a measurable statement about residuals that remain after the orbit is well constrained, after systematic effects are tested, and after the measurement chain is examined. The arc length becomes the anchor, and the object's continued presence in predicted sky positions becomes the proof that tracking is not drifting. Only then can the focus move inward from the process of observation to the meaning of the deviations that remain. A trajectory is spoken of as if it is a single line carved into space, but in practice, it is a relationship between measurements, a model, and time. In the observational record, the object never displays its full path at once. It offers positions at moments, and each position carries uncertainty. The model turns those positions into a predicted curve that can be projected forward and backward. When a report says the object altered its trajectory, the statement can mean two very different things. One meaning is ordinary and expected. The trajectory estimate changes because the information improves. The other meaning is physical. The object's motion changes because an additional force acts on it. The work in this region is to keep these meanings separate because they can look similar from the outside while being fundamentally different in cause. An information-driven change happens when the orbit solution is updated after new data arrive. Early in tracking, the orbit can shift noticeably with each new night because the uncertainty is wide and the data arc is short. A revised estimate can move the predicted future position by large amounts without any physical change having occurred. The object follows one path in space, while the computed path, the best fit under gravity, evolves as uncertainty shrinks. This can be especially dramatic when the object is first observed near a geometry that hides distance, such as when the line of sight changes little from night to night. When distance is poorly constrained, speed and distance can trade off in the fit. As the observing geometry improves, the fit settles into a narrower range and the predicted path can shift. Such shifts are not evidence of a deflection. They are evidence that the earlier estimate lacked leverage. A physical change, by contrast, is not a change in the best fit parameters caused by new data. It is a persistent mismatch between data and a well-constrained model. In that case, new data do not merely refine the orbit. They reveal that the orbit under the assumed forces cannot pass through all the observed positions at their times without leaving systematic residuals. The key word is systematic. Random scatter around the model is expected. Systematic offsets that grow with time or that align in a pattern indicate that something consistent is being missed. In precise orbit work, a small persistent acceleration can cause the predicted positions to drift gradually away from the observed ones. If the object is repeatedly found near the edge of the predicted uncertainty region rather than near its center, and if this persists after the uncertainty is already small, the difference becomes meaningful. The term altered trajectory is also used informally when observers notice a sudden revision in predicted positions. A sudden revision can happen for mundane reasons. One reason is the discovery of a measurement error in earlier data such as a timestamp mistake or a misidentified star used in the reference frame. Another reason is that an early observation is later recognized as belonging to a different object, a false linkage that pulls the orbit toward the wrong solution. When that linkage is removed, the orbit can jump. A third reason is the addition of high-precision data that dominate the weighting. If earlier data are noisy and then a set of sharp measurements arrives from a larger telescope under excellent conditions, the orbit can shift to accommodate the new information. The shift is not a physical turning. It is a recalibration of knowledge. A useful way to define a trajectory change is to ask what remains invariant. In gravitational motion, the state of the object at a given time, its position and velocity determines its future under the chosen force model. If the model includes only gravity, and if the measurements are accurate, then a single state exists that can match all positions within their uncertainties. If no such state exists, something must be added or corrected. The added element could be a force such as a small acceleration that depends on distance from the sun. It could also be a correction to the measurement process, such as a bias that shifts positions in one direction. In both cases, the trajectory under the original assumptions is not adequate. The distinction is found by testing alternatives and checking whether the residual pattern behaves as a force would behave. A physical alteration also has an implication in time. A force that acts continuously produces a smooth deviation that accumulates gradually. A sudden impulse like deflection would produce a kink, a change in velocity over a short time. In most small body contexts, sudden impulses are rare and difficult to prove from angular positions alone because the observational cadence may miss the exact moment. More commonly, non-gravitational forces act over days and weeks, and their imprint is a gentle drift in residuals. The change is not that the object abruptly turns. The change is that the gravitational prediction slowly falls behind or runs ahead. The word altered can mislead if it suggests a dramatic deviation. The actual evidence usually appears as a small, persistent offset that becomes visible only because measurement precision and arc length are sufficient. The interpretation is further complicated by the way astrometry measures a light distribution rather than a solid surface. If the object develops a coma or a tail, the brightest region can shift relative to the nucleus. If the coma brightens on one side due to sunward jets, the centroid can move slightly. This produces a false trajectory change because the measured positions trace the shifting center of light rather than the center of mass. The effect can mimic a non-gravitational acceleration, especially if the asymmetry is tied to the sun direction and repeats as the object rotates. Distinguishing this from a real force requires careful comparison with imaging that resolves the coma structure and with techniques that attempt to locate the nucleus within the coma. The point in this region is that a trajectory is inferred from positions, and positions can be biased by appearance. The phrase physics cannot explain it often appears when the public hears that a gravitational fit does not match the data. Within careful analysis, the statement is usually narrower. It might mean that a gravity-only model leaves residuals larger than expected. It might mean that the standard comet non-gravitational model, often tuned for typical outgassing behavior, does not capture the residual pattern. It might mean that the direction of the inferred acceleration is unusual relative to the sunline. Each of these is different. None of them immediately implies a violation of physical law. They imply that the current model set is incomplete, or that assumptions about the object's behavior are not yet adequate. Physics includes many small forces that are well understood, but difficult to quantify for a specific object without additional observations. To decide whether an apparent alteration is informational or physical, analysts perform consistency checks that remain within this outer interpretive layer. They refit the orbit with different subsets of data to see whether the deviation depends on a particular telescope or a particular time window. They examine residuals as a function of sky position to see whether catalog biases might be present. They check whether residuals correlate with brightness, because a correlation suggests that changes in appearance affect the measured center. They compare results using different astrometric reduction pipelines, because a pipeline-specific bias can produce a consistent offset. They test whether the residual pattern follows the direction expected for solar radiation pressure or for outgassing. These tests do not prove a cause by themselves. They narrow the space of plausible causes and clarify what is being claimed. A particularly important concept is the difference between a model parameter shift and a force detection. A parameter shift happens when adding more data changes the best fit orbital elements. This can occur even with perfect physics because the earlier fit is uncertain. A force detection happens when adding a force term improves the fit in a statistically meaningful way and reduces systematic residuals across independent data sets. The force term is not introduced merely to make the model flexible. It is introduced because the residuals exhibit a coherent structure consistent with an acceleration. In careful practice, the introduction of such terms comes after demonstrating that the gravitational baseline is complete and that measurement systematics are not likely to produce the observed pattern. In this region, altered trajectory becomes a disciplined phrase. It refers to a mismatch between a well-established baseline prediction and a robust set of observations beyond what uncertainty can plausibly cover. It does not refer to the ordinary updating of an orbit as the observation arc grows. It does not refer to a dramatic turning in the sky. It refers to residual behavior that persists when the orbit is already secure, and that remains after the measurement chain is audited. Only when that definition is held steady can later layers the forces that might cause the deviation be approached without confusion. For now, the focus remains on meaning what is actually being asserted when motion is said to change, and what must be demonstrated before the assertion shifts from a revision of knowledge to a claim about additional forces acting on a small body moving through space. The baseline for judging any claimed deviation is a model that assumes gravity does the work, and does it in a way that is as complete as practical. In this region, the object is treated as a test mass, small enough that it does not significantly influence the motion of planets, yet large enough to be followed as a single body. The model begins with the Sun, whose gravity dominates the inner solar system and still shapes motion far beyond it. Under the simplest assumption, the object follows a conic section around the Sun, with its speed increasing as it falls inward and decreasing as it climbs outward. That ideal picture is useful, but it is not the full baseline used in precise tracking. The full baseline adds the gravitational pulls of the planets and other known massive bodies because even a weak tug applied over long spans of time can shift where the object is expected to appear on the sky. The starting point is a reference time at which the object has a position and a velocity in a chosen coordinate frame. That frame is usually centered in a way that makes the gravitational problem stable and consistent across many objects. In a sun-centered frame, the sun sits at the origin and the planets move around it, while the small body moves through the combined gravitational field. In a solar system barycenter frame, the origin is near the system's center of mass, and the sun itself moves slightly. Both frames can be used, and transformations between them are well understood. But what matters in practice is that the same choice is used consistently in the integration and in the conversion to predicted sky positions. The baseline model includes the ephemerides of the planets, meaning the computed positions and velocities of those planets as a function of time based on long-term tracking and dynamical models. The object's motion is then integrated forward and backward in time under the combined gravitational accelerations. Gravity in this baseline is not a single equation written in isolation. It is a continuous computation that accounts for changing distances. The pull from a planet depends on how far the object is from that planet at each moment, and that distance changes as both bodies move. For an object that remains far from the planets, the planetary terms act as gentle background perturbations. For an object that passes closer, the effect can become much stronger and can bend the trajectory in a way that is both predictable and measurable. The baseline, therefore, includes close approach, screening and assessment of whether the path brings the object near any major body, because close approaches can dominate the later orbital evolution and can also produce apparent anomalies if a close approach is missed or mischaracterized. The sun's gravitational field is not the only source of predictable deviation from a pure two-body conic. The sun is not a perfectly uniform sphere in a strict mathematical sense, but for most small-body orbit work, the sun's higher-order gravitational features are negligible compared with other terms. What is often more relevant is that light does not travel through a static Euclidean space in the vicinity of the sun. The path of light is slightly bent, and the timing of light travel is slightly altered by the curvature of space-time associated with massive bodies. In high precision, astrometry corrections for these effects are included so that the predicted direction from Earth to the object matches how light actually propagates. These corrections are not introduced as speculative ideas. They are standard parts of precise celestial mechanics and are validated by many independent measurements across decades. Their role in the baseline is straightforward: remove known small shifts so that any remaining residuals do not arise from omitted established physics. Earth's role in the baseline is twofold. Earth is a gravitating body that slightly perturbs the small body's trajectory, and Earth is the moving platform from which observations are made. The baseline includes Earth's gravity as part of the planetary system, but it also includes the precise position of the observing site relative to Earth's center at the time of observation. Earth rotates, and Earth's axis slowly wobbles, and Earth's rotation rate is not perfectly constant. These effects are tracked and modeled so that the transformation from an Earth surface coordinate to an inertial direction in space is accurate. When the baseline is built carefully, the predicted topocentric direction, meaning the direction as seen from a specific observatory, accounts for Earth's rotation, the observer's location, atmospheric refraction corrections, applied in the reduction pipeline, and the light-time geometry. The aim is that the gravitational model yields not only a path in space, but a prediction for where the object should appear in the sky images at given times. The baseline model also depends on what is assumed about the object itself. In the gravitational-only baseline, the object is treated as if its center of mass follows the computed path. This is an assumption about dynamics, not about appearance. It does not assume the object is spherical, reflective, active, or inactive. It assumes only that no significant forces other than gravity are acting, and that the observations trace the object's position consistently. This is why the earlier regions emphasize measurement chain audits. If the observed position traces a shifting center of light rather than the center of mass, the gravitational baseline can appear wrong, even when the dynamics are purely gravitational. The baseline therefore gains strength when imaging shows a point-like appearance or when astrometric methods are used that track the nucleus position as reliably as possible. To compute the baseline trajectory, the integration must step through time in small increments. At each step, the gravitational accelerations from the Sun and planets are evaluated based on current positions. The result is a new velocity and a new position. Over the full time span of interest, this produces an integrated orbit that can be compared to observations. The comparison is not done in the space coordinates directly because observations are angular. Instead, the integrated position of the object is combined with the integrated position of Earth and the line of sight vector. From observer to object is computed for each observation time, including the light time correction that aligns the object's state to the emission time rather than the reception time. That line of sight is then converted into a predicted right ascension and declination that can be directly compared with measured astrometry. In a clean gravitational baseline, residuals should look like noise around zero, meaning they should scatter with no drift and no repeated structure. Some scatter is expected because measurement errors are unavoidable. The size of that scatter should match what is known about the instruments and reduction quality. When residuals exceed those expectations, the baseline is challenged. Before moving inward to consider additional forces, the baseline is stress-tested. Analysts may change the set of planetary ephemerides used or confirm that the chosen ephemerides are appropriate for the time span and precision needed. They may test whether including additional bodies, such as the largest asteroids, changes the predicted positions at a meaningful level. For most cases, the largest corrections come from the major planets. But in sensitive situations, small contributions can matter, especially if the object passes through regions where the gravitational environment is subtly complex. Another stress test concerns the reference frame. A baseline in one frame must produce the same predicted sky positions as a baseline in another frame after correct transformations. If a discrepancy arises, it indicates an implementation problem rather than new physics. Similarly, the baseline depends on the timescale used for integration and for observation times. If timestamps are interpreted in a scale that is offset from the scale used in ephemerides, small drifts can appear. A careful baseline aligns these scales and checks that the transformation from recorded observation time to the time used in the dynamical model is correct. This work is quiet and technical, but it is essential because an unexplained residual can be manufactured by a misalignment between time standards or by a subtle error in the observer location transformation. When the baseline is sound, its predictions become the reference against which any claimed alteration is defined. A trajectory alteration in the physical sense is then framed as an additional acceleration that must be added to the baseline to bring predicted and observed positions into agreement. That acceleration may depend on distance from the Sun, on the object's orientation, or on other properties, but the baseline must first demonstrate that it is not missing any known gravitational ingredient. If a close approach to a planet occurs, the baseline should predict a sharp bend at the correct time. If the object remains far away, the baseline should predict a smoother path. If the object approaches the Sun, the baseline should include the small but known corrections relevant to light propagation and gravitational dynamics near a massive body to the extent required by the measurement precision. In this region, gravity is not treated as a vague concept. It is a concrete prediction pipeline that starts with a chosen state, integrates motion under known masses, converts integrated positions into predicted sky directions as seen from Earth, and produces residuals that can be evaluated for structure. The baseline is not an attempt to prove that gravity explains everything. It is an attempt to remove every ordinary and well-understood contribution so that what remains, if anything remains, can be discussed with clarity. Only once the gravitational baseline has been built and tested can the discussion move inward toward the subtle forces that can mimic anomalies and toward the careful language that distinguishes a mismatch in a model from a failure of physics itself. With a gravitational baseline established, attention turns to the residuals, the differences between where the object is observed to be and where the model predicts it should be. Residuals are not an afterthought. They are the diagnostic signal that tells analysts whether the model and the data are in harmony. A residual is computed for each observation by taking the predicted sky position at that observation time and subtracting it from the measured position. The result is a small, angular offset on the sky. When residuals are scattered randomly around zero with a spread consistent with measurement uncertainty, the model is adequate at that level of precision. When residuals show a pattern, the pattern carries information. It can point to remaining measurement systematics, to missing terms in the physical model, or to the fact that the object's measured position does not track its center of mass consistently. Residuals are usually examined in two components, corresponding to directions on the sky. Even without naming the technical axes, the idea is simple. One component is along an east-west direction in the sky coordinate system, and another is along a north-south direction. A pattern can appear in one component or in both. A steady drift in one direction over time suggests that predicted positions are gradually diverging from observations. A sinusoidal pattern may suggest a periodic influence, such as an unmodeled effect, tied to Earth's rotation, the object's rotation, or an instrument's nightly behavior. A cluster of residuals from one observatory that sit consistently offset from zero suggests a local systematic bias. Residuals, therefore, are plotted against time, against observing geometry, and against observational source. One of the first checks is whether the residuals are dominated by a subset of data. If observations from a single telescope show a consistent offset while others do not, the cause is more likely in that telescope's calibration or reduction pipeline. If all telescopes show the same drift, the cause may lie in the physical model or in a shared reference catalog. Another check is whether residuals change with brightness. If the object becomes brighter and residuals increase or shift systematically, at the same time it raises the possibility that the object's appearance is changing in a way that biases astrometry. If residuals are stable across brightness, changes' appearance bias becomes less likely, though it cannot be dismissed without imaging analysis. Residuals are also examined as a function of air mass, the amount of atmosphere the telescope looks through. If residuals worsen at low altitude, atmospheric refraction corrections may be imperfect. The pattern of residuals can also be translated into an implied acceleration. If the object appears consistently ahead of its predicted position along its orbit, it may have experienced a small additional acceleration in the direction of motion, or the model may slightly underestimate its speed. If it appears behind, the opposite may be true. If residuals point roughly toward or away from the Sun, they may suggest a force that is tied to solar direction, such as outgassing thrust, radiation pressure, or thermal recoil. The relationship is not one-to-one because residuals are angular and depend on viewing geometry, but with a long arc and good coverage, analysts can infer the direction and magnitude of any extra acceleration required to reduce the residual pattern. Not all patterns point inward to new forces. Some point outward to the measurement chain. A common source of subtle structure is the star catalog used to define the reference frame. If the catalog has small regional distortions, residuals can show a dependence on where the object lies on the sky. As the object moves into a new star field, the reference frame changes. A systematic offset may appear to start at a certain date, but the real cause could be that the object entered a region where catalog biases differ. Another source is differential chromatic refraction, an atmospheric effect, where blue and red light refract slightly differently. Stars of different color can have slightly different apparent positions at low altitude. If the object's color differs from the average reference stars, a small bias can occur, especially when observations are taken at high air mass. This can create residuals that correlate with altitude and with filter choice. Residuals can also reflect timing issues. If an observatory's timestamps are slightly offset, the predicted position for the recorded time will differ from the object's actual position at the true time, producing a systematic residual. The sign and magnitude depend on the object's angular speed. For fast-moving objects, even a small timing offset can produce a noticeable positional shift. A timing error can mimic a non-gravitational acceleration if it varies over time or differs between instruments. This is why analysts compare residuals from different observatories and examine whether the offset scales with apparent motion rate. If an offset scales in that way, timing is suspect. When residuals persist after these checks, analysts may fit a non-gravitational term. This is still within the residual region because the question remains diagnostic: what additional term reduces the pattern? The fitted term is often parameterized as an acceleration with a dependence on distance from the Sun, because many physical processes are controlled by solar heating. The act of fitting such a term does not prove the physical cause. It tests whether the residuals behave like the imprint of a continuous acceleration. If the term reduces residuals across the whole data set, and if it improves predictive accuracy for future positions, it becomes a strong hint that a real force is present. If the term only improves the fit over a narrow interval or only for one observatory, it is less compelling and may indicate overfitting or data issues. The phrase "physics cannot explain it" sometimes arises when residuals remain even after a standard non-gravitational term is added. This can happen for several reasons that are still consistent with ordinary physics. The standard parameterization may be too simple for the object's behavior. Outgassing can be directional, episodic, and dependent on rotation. A single smooth distance-dependent term may not capture such complexity. The object may be tumbling, causing thrust direction to change. The object may have multiple active areas that turn on and off. Dust emission can shift the center of light in a way that is not simply tied to distance from the sun. In these cases, residuals can persist because the model does not represent the complexity, not because physical laws have failed. A careful residual analysis also examines whether deviations are compatible with observational cadence. If a residual pattern suggests a sudden change, analysts ask whether such a change could be resolved by the existing observation times. A sharp kink in residuals may indicate that a subset of observations is biased rather than a true impulse. Alternatively, it may indicate an event such as fragmentation or a sudden outburst that changes the object's appearance and therefore its measured center. Distinguishing these requires looking at imaging and photometry around the time the residuals shift. A sudden brightening accompanied by a sudden residual change suggests an outburst or morphological change. A residual change without photometric change suggests a different cause. Residuals are also evaluated statistically. The distribution of residuals should match the assumed error model. If residuals are consistently larger than expected, the uncertainties may be underestimated. If residuals show heavy tails, it may indicate occasional outliers or correlated noise. Analysts may inflate uncertainties or adjust weights to reflect this. The goal is not to make residuals look good. The goal is to use a realistic uncertainty model so that conclusions about extra forces are not driven by an overly optimistic estimate of measurement precision. In a mature analysis, the claim of an unexplained deviation is accompanied by a careful statement of how significant the deviation is relative to realistic uncertainties. In this region, the object's story is written in small numbers. A tiny angular offset repeated consistently can indicate a real physical effect, but only if it survives every test of systematic bias. The pattern in the residuals is the map that guides the next inward steps. If the pattern points, sunward forces tied to solar heating become candidates. If the pattern points along the track, thrust or timing issues become candidates. If the pattern shifts with starfield catalog bias becomes a candidate. The residuals are therefore the crossroads between observation and physics. They do not yet name the cause, but they define what must be explained and with what level of precision. When the residual pattern is stable, coherent, and robust across instruments, it becomes reasonable to move inward towards specific non-gravitational mechanisms. When the pattern is fragile or instrument-dependent, the path inward remains blocked by the need for better data and cleaner reductions. Either way, the residuals are where a claim of altered trajectory becomes a measurable statement rather than a dramatic phrase, and where the next layer of explanation must begin with what the data actually demand. Before any inward move toward subtle forces, the first inward step from residual patterns is a full audit of the measurement chain, because many apparent anomalies are born in how light becomes numbers. An instrumental or reduction pitfall is not a minor nuisance. It can generate coherent residuals that mimic physical accelerations. The audit begins at the detector itself. A camera records light as electrons in pixels, and each pixel has its own quirks. Some pixels respond slightly differently to the same amount of light. Some have higher noise. Some have defects. Calibration frames are used to correct these issues, but calibration is never perfect. If a flat field correction is slightly off, the measured centroid of a faint object can shift depending on where it falls on the detector. As the object moves across the field night after night, such shifts can produce a pattern that looks like a drift in position, even though the object's true direction has not changed. The next layer is the optical system. Telescopes have distortions that change across the field of view. These distortions are modeled in the astrometric solution, but their exact form can vary with temperature focus and mechanical flexure as the telescope points to different parts of the sky. If the distortion model is too simple, residuals can become position-dependent within the detector. A moving object observed near the edge of the field may be measured with a slightly different bias than when it is observed near the center. If early observations come from one part of the detector and later observations come from another, the orbit fit can be pulled in a way that produces an apparent anomaly. This is why refined analyses often record not only the sky positions, but also the detector coordinates and observing conditions, allowing patterns to be traced to specific parts of the hardware. Timing is another pitfall with an outsized impact. The reported time of an exposure may refer to the start of the exposure, while the effective time for astrometry is closer to the midpoint, because light accumulates over the whole exposure. If the camera shutter does not open and close instantly, or if the exposure time is not precisely what is recorded, the midpoint can be shifted. In high-cadence survey, work timing is usually well controlled, but errors can happen. A timing offset acts like a shift along the direction of motion because the object is assumed to be where it would be at the recorded time. The faster the object's apparent motion, the larger the positional error for a given timing error. This creates a diagnostic signature residuals that scale with angular speed and align with the direction of motion suggest timing problems. If such a signature appears in data from one observatory, but not others, the timing system of that observatory becomes a prime suspect. Atmospheric effects are a major source of subtle bias. Refraction shifts apparent positions toward the zenith, and the correction depends on pressure, temperature, humidity, and the object's altitude. Pipelines often apply standard refraction corrections based on typical conditions, but local weather can vary. More subtle is differential chromatic refraction, where the atmosphere refracts different wavelengths by slightly different amounts. Stars have different colors, and the moving object can have a color that differs from the average. If observations are taken at low altitude, The color-dependent refraction can shift the object's centroid relative to the reference stars in a way that depends on filter and on the object's spectral slope. This shift can be systematic across a night and can repeat on multiple nights if the object is observed at similar altitudes. The pitfall here is that the effect can masquerade as a physical acceleration tied to the sun direction, because the observing geometry relative to the horizon can correlate with the object's position relative to the sun in the sky. Star catalogs and reference frames are another deep source of pitfalls. Modern surveys use large catalogs with precise star positions and proper motions. Proper motion is the slow movement of stars across the sky over years. If a star's proper motion is slightly wrong, its catalog position at the observation date is slightly wrong. When many such stars are used to anchor the astrometric solution, small errors can average out, but regional systematics can remain. For example, if the catalog has a slight distortion in a patch of sky, then all objects measured against that patch will inherit a bias. As the moving object travels through different star fields, it can pass from one bias regime to another. This produces a step-like change in residuals that can look like a sudden alteration in trajectory. The diagnostic again is dependence on sky region rather than on time alone. Analysts test this by re-reducing the images with different catalogs when possible, or by comparing the object's residual behavior to that of other known objects measured in the same fields. The reduction pipeline itself can introduce assumptions that matter. One common assumption is how to model the point spread function, the shape of a star image on the detector. If the model is symmetric, but the true shape is slightly asymmetric due to tracking wind shake or optical aberrations, centroid estimates can be biased. For faint objects, the bias can be larger because noise interacts with the model fit. Another assumption is how to handle trailing. If the object is trailed, its centroid along the trail can be biased, depending on how the trail is modeled. If the trail is short, it may be treated as a point producing a slight position shift. If it is long, it may be modeled as a line. Different pipelines do this differently. A mismatch in approach between survey data and follow-up data can create systematic differences that appear as residual patterns. Blending with background sources is a pitfall that can be hard to detect. The object can pass near a background star or galaxy. If the object overlaps the background source, the combined light distribution shifts, and the measured centroid is biased. This can happen even when the background source is faint and not obvious in a single image. The result can be an outlier or a cluster of biased points if the object passes through a crowded region over several nights. If those points are not identified and down-weighted, they can pull the orbit solution. In extreme cases, the orbit fit may attempt to accommodate them by introducing a spurious acceleration. Analysts check for this by examining image cutouts around each observation and by cross-matching the object's path with catalogs of background sources. Another subtle pitfall comes from the object itself when it is not a clean point. If it has a coma or a tail, the centroid depends on how the coma is distributed and on how the measurement algorithm defines the center. A sunward jet can brighten one side of the coma, shifting the centroid away from the nucleus. If the jet strength changes with solar heating, the centroid shift can change with heliocentric distance. This can mimic a non-gravitational acceleration, but it is not a change in the center of mass motion. It is a measurement artifact tied to the evolving brightness distribution. Disentangling this requires higher resolution imaging, sometimes with larger telescopes or different observing techniques to locate the nucleus more directly. The audit of pitfalls ends not with a single correction, but with robustness. Analysts ask whether the anomaly persists when they restrict the data to the highest quality subset. They ask whether it persists when they exclude observations taken at high air mass, or when the object is near the edge of the detector, or when the background is crowded. They ask whether different reduction pipelines produce the same residual pattern. They look for the same pattern in independent observatory data. If the anomaly disappears under these tests, it is likely a measurement chain effect. If it persists, and especially if it persists across independent systems, then the path inward toward physical non-gravitational forces becomes justified. In this region, the phrase physics cannot explain it becomes more precise again. A mismatch between a model and data is not automatically a failure of physics. It is often a reminder that measurements are complex and that the translation from photons to coordinates contains many small choices. A careful audit narrows those choices. It either identifies a bias that can be corrected, or it increases confidence that the residual pattern reflects a real acceleration. Only after this audit does it become responsible to treat the residuals as a dynamical signal rather than an artifact. The inward path therefore passes through instruments and pipelines first, because the outermost source of apparent mystery is often the quiet complexity of how the sky is measured. After the measurement chain is audited, the next inward layer considers non-gravitational forces that are already part of standard small body dynamics, beginning with outgassing. Outgassing is the release of gas from volatile material when sunlight warms an object. In cold outer regions, certain ices can remain stable. As the object approaches the sun, the surface and near subsurface warm, and some ices can sublimate, meaning they pass from solid to gas without becoming liquid. The gas escapes through pores and fractures, and it can carry dust with it. This process builds a coma and sometimes a tail. It also produces thrust. The escaping gas carries momentum, and conservation of momentum requires that the nucleus receives an equal and opposite push. The push is usually tiny compared to gravity, but because it can act continuously over long intervals, it can produce measurable changes in motion. Outgassing thrust depends on several conditions. It depends on heliocentric distance, because sunlight intensity increases closer to the sun. It depends on which volatiles are present, because different substances sublimate at different temperatures. Water ice becomes strongly active closer to the sun, while more volatile substances can drive activity farther out. It depends on how heat is transported into the surface, which is influenced by thermal conductivity, porosity, and the presence of insulating dust layers. It also depends on the geometry of active areas. If activity is uniform over the whole surface, thrust can cancel out in different directions, producing little net acceleration. If activity is concentrated in jets or localized patches, the net thrust can be significant, and its direction can vary as the object rotates. The direction of the outgassing thrust relative to the sun is often important. Sunlight heats the sunward side more strongly, so activity often originates there. Yet the maximum gas release may lag behind the subsolar point, because the surface takes time to heat, and because heat penetrates to a depth where ices sublimate. This lag means the thrust direction can be rotated relative to the direct sun line. For rotating bodies, active areas move in and out of sunlight, and the resulting thrust averages over a rotation period. If the object rotates regularly, the average thrust can be stable. If the object tumbles or has a complex rotation, the thrust direction can change in more complicated ways. This is one reason standard orbit models sometimes struggle. A simple parameterization that assumes a smooth dependence on distance to the Sun and a fixed thrust direction can be inadequate for an object with irregular activity. To connect outgassing to trajectory, analysts use non-gravitational force models that introduce additional acceleration terms into the orbit integration. These terms are often expressed in components aligned with the object's orbital frame, such as radial transverse and normal directions. The radial component points toward or away from the Sun. The transverse component points along the direction of motion, and the normal component points out of the orbital plane. The model then assumes that each component scales with a function of heliocentric distance that approximates how sublimation varies with solar heating. The parameters are fitted to the residuals. If the fitted parameters reduce systematic residuals across the data set and improve predictions, the model is supported as a description of the motion, even if the exact physical details of jets remain unknown. Outgassing also has observational signatures beyond astrometry. A coma can be detected as an extended light distribution around the nucleus. A tail can appear, often pointing away from the Sun due to radiation pressure acting on dust, though gas tails can have different orientations. Photometry can show increased brightness as activity rises. Spectroscopy can detect emission features from certain molecules or radicals that form when sunlight breaks apart parent molecules. None of these signatures is guaranteed. A weakly active object can produce thrust with little visible coma if the gas production is low and the dust content is minimal. Conversely, a dusty coma can be bright, while the net thrust is modest if activity is distributed in a way that cancels. The inference is therefore cautious. Thrust can be present without a dramatic visual display, and a visual display does not uniquely determine thrust magnitude. An important inward step is to distinguish actual outgassing thrust from centroid shifts caused by coma asymmetry. Both can occur together. If a jet produces thrust, it also produces an asymmetric coma. The asymmetric coma can shift the measured position of the object's center of light, creating an astrometric bias that may either reinforce or oppose the dynamical effect. In careful work, analysts attempt to measure the nucleus position within the coma, or to correct for expected centroid shifts. High-resolution imaging can help. So can using measurements taken in wavelengths less affected by gas emission, or using techniques that fit the inner coma profile to estimate where the nucleus lies. The goal is to ensure that the astrometry traces motion of the mass, not merely motion of the brightest dust. Outgassing behavior can also be episodic. A pocket of volatile material can be exposed suddenly as sunlight warms a weak surface layer. A small landslide, a crack opening, or a local collapse can expose fresh ice. This can cause an outburst, a sudden brightening, and increased gas release. An outburst can change thrust temporarily, producing a deviation that may look like a change in trajectory. If the outburst is short relative to the observation cadence, its dynamical effect may resemble a small impulse. More often, the effect is spread over days as the exposed material continues to sublimate. The residual pattern may then show a change in slope rather than a sharp kink. Observers look for coincident photometric changes to support this interpretation. But again, detection depends on observing conditions and sensitivity. The physical plausibility of outgassing also depends on the object's origin and history. A long-lived asteroid that has spent many orbits near the Sun may have lost most near-surface volatiles. A newly arrived object from colder regions may retain more volatiles. Yet even in the inner solar system, some bodies can preserve volatile pockets beneath insulating layers, and impacts can expose them. The inference remains based on evidence. A fitted non-gravitational term that resembles outgassing and is accompanied by morphological or photometric signs strengthens the case. A fitted term without such signs remains possible but less certain, and it invites deeper checks of other forces and of measurement biases. When an anomaly is described as unexplainable, outgassing is often the first conventional mechanism considered because it is known to alter trajectories measurably. The phrase "physics cannot explain it" may reflect that a simple outgassing model fails to match the residual pattern, or that the inferred acceleration direction does not align with typical outgassing expectations. But atypical does not mean impossible. Outgassing can be anisotropic delayed seasonally modulated by rotation axis orientation and altered by surface evolution. A highly oblique rotation axis can cause one hemisphere to receive more sunlight over a season shifting activity patterns. A tumbling state can cause the thrust direction to vary. A jet from a localized region can produce a thrust component out of the orbital plane, leading to normal acceleration. Such complexity can challenge simplified models and produce residuals that persist unless the model is made more detailed. The inward motion in this region remains grounded. Outgassing is not an exotic idea. It is a process observed across many comets and active asteroids, and it is a known contributor to orbital evolution. The question is not whether outgassing exists as a physical process. The question is whether the specific pattern of residuals in this case is consistent with a realistic outgassing scenario, given the observed appearance and brightness behavior. This requires integrating astrometry with physical observations, and it requires resisting the temptation to treat any mismatch as evidence that laws have failed. Instead, outgassing provides a framework that can be tested, refined, or rejected based on whether it improves predictive accuracy and whether it aligns with what is seen in the object's emitted and reflected light. Moving inward from gas-driven thrust, another class of non-gravitational influence comes from light itself and from the dust that light can push. Sunlight carries momentum. When sunlight is absorbed or reflected by a particle or a surface, momentum is transferred, and a force results. For large bodies, the force is usually negligible compared to gravity. For very small bodies and for dust grains, it can be significant. In orbit analysis, this influence appears in two related ways: direct radiation pressure acting on the object, and radiation pressure acting on dust released from the object, which can then alter the observed appearance and measured position. Both mechanisms can produce apparent or real deviations from a purely gravitational path, and both depend strongly on size, shape, and surface properties. Direct radiation pressure on a compact body is simplest to understand as a steady push away from the sun. The force depends on the cross-sectional area that intercepts sunlight and on how efficiently the object absorbs or reflects that light. The acceleration depends on the force divided by mass. This means that for a given area, a lower mass produces a larger acceleration. Small, low-density objects therefore experience more noticeable radiation pressure acceleration than large, dense ones. If an object is very small, perhaps a meter-scale fragment radiation pressure can be measurable. For kilometer-scale bodies, it is usually tiny. Yet size is not always known precisely from brightness alone, because brightness depends on reflectivity and on whether the object is surrounded by dust. A faint object could be small and reflective, or larger and dark or active with dust that increases brightness without increasing mass. This uncertainty complicates the evaluation. Radiation pressure also depends on the distance from the sun. Sunlight intensity decreases with the square of distance. The radiation pressure force follows the same dependence. This makes the effect stronger closer to the sun. If residuals show a pattern that increases as the object approaches the sun, radiation pressure becomes a candidate. But outgassing and thermal recoil also increase with solar heating, so the distance dependence alone does not distinguish them. Direction helps. Radiation pressure acts primarily away from the sun. Outgassing can have a thrust direction offset by rotation and thermal lag. Thermal recoil can act in directions related to spin and surface temperature distribution. Analysts therefore look at the direction of the inferred acceleration relative to the sun and relative to the velocity vector. A key subtlety is that radiation pressure on a solid body acts on the surface, while the object's orientation can change. If the object is elongated and rotates, the projected area facing the sun changes, causing the force to vary. The average over time may still be away from the sun, but the magnitude can fluctuate. For a tumbling object, the fluctuations can be irregular. This could produce residual patterns that are not well captured by a constant coefficient model. In principle, if the rotation state is known from light curve observations, the radiation pressure modulation could be modeled more accurately. In practice, such detailed modeling is difficult unless the data set is rich and the object is bright enough for precise photometry. Radiation pressure acting on dust is often more visible. When an active object releases dust, the dust grains are pushed away from the sun, forming a dust tail. The dust tail shape is controlled by the balance between gravity and radiation pressure on each grain. Small grains are pushed more strongly and form broader, more curved tails. Larger grains are less affected and remain closer to the object's orbit. The dust does not significantly change the nucleus trajectory by itself because the dust separates from the nucleus. However, the presence and distribution of dust can strongly affect astrometry. If the dust is concentrated on one side, the center of light shifts. The object's measured position then reflects a weighted average of nucleus and dust. This can create apparent accelerations in residuals that are not dynamical. The bias can be particularly strong when the nucleus is faint relative to the coma. A small nucleus surrounded by a bright dust cloud can be very difficult to locate precisely. There is also a dynamical coupling through mass loss. When dust and gas leave the nucleus loses mass. Mass loss by itself does not cause acceleration unless it is directional, but it can change how radiation pressure and thermal effects act, because it changes the mass and potentially the surface properties. In addition, if dust loss is highly anisotropic, it reflects underlying anisotropic outgassing or mechanical ejection that does impart thrust. In this sense, dust is both a tracer and a contributor. It traces the activity that may be pushing the nucleus, and it contributes to the observed appearance that can bias the measured position. To assess radiation pressure, analysts often consider the area-to-mass ratio implied by the measured acceleration. A small acceleration away from the Sun can be produced by radiation pressure if the object has a sufficiently large area per unit mass. For a typical dense rock, the area-to-mass ratio is small, so the acceleration would be tiny. For a very low-density object, perhaps porous, or for a thin fragment with a large surface area, the ratio could be larger. Yet such inferences are uncertain because mass is not directly measured. Brightness can be converted to an approximate size only with assumptions about reflectivity and phase function, the way brightness changes with viewing angle. If the object is active, brightness is dominated by dust and gas, and the nucleus size could be much smaller than implied by brightness. This opens a wide range of possible area-to-mass ratios. Analysts therefore treat radiation pressure as plausible or implausible only after considering whether the object appears point-like, whether a coma is detected, and whether the brightness behavior suggests a compact body. Another subtle mechanism related to light is the Poynting-Robertson effect, a drag-like force that causes dust grains to spiral inward over long times. For small body orbit anomalies on timescales of months, this effect is usually too small to matter for the nucleus, but it can matter for dust evolution and for how a tail appears. Tail evolution, in turn, affects measured centroid positions. Again, the dynamical effect on the nucleus is minimal, but the observational effect can be non-trivial when the nucleus is embedded in a dust cloud. The lesson is that light can matter either by pushing the nucleus directly or by shaping the dust distribution that biases the measurements. Radiation pressure and dust effects are also tied to the phase angle. The phase angle is the angle between the Sun, the object, and the observer. At small phase angle, the object can appear brighter due to backscattering properties of dust and surface. At larger phase angles forward, scattering by dust can dramatically increase brightness, especially for fine grains. This can make an object appear to brighten unexpectedly as geometry changes. Such brightening can be misinterpreted as increased activity. If increased brightness is actually due to scattering geometry, then assumptions about dust production may be wrong, and the inferred thrust from outgassing may be misestimated. Conversely, if brightness changes are truly due to increased dust production, then the coma can become more prominent and astrometric biases can change. Analysts therefore interpret photometric changes with awareness of phase angle effects, separating geometric scattering from genuine production changes as far as possible. In the context of an altered trajectory, claim radiation pressure becomes a candidate particularly when the inferred acceleration is directed away from the Sun and scales smoothly with solar distance. Yet the same signature can be produced by an astrometric centroid shift caused by a dust tail that grows and changes orientation relative to the line of sight. A dust tail points roughly away from the Sun, so the center of light can be displaced in that direction. If the displacement changes with time as dust production changes, it can mimic a sunward or anti-sunward acceleration. Disentangling these possibilities requires comparing astrometric residuals to resolved images of the coma and tail if available, and testing whether the residuals depend on measurement aperture and centroid algorithm. If changing the aperture changes the measured position, it suggests that extended dust is influencing the centroid. This inward region therefore treats light as both force and confounder. Radiation pressure is a real physical force that can alter motion for small, low-mass objects. Dust shaped by radiation pressure can also alter the apparent position measured by telescopes. In either case, the baseline gravitational model is not enough. Yet the explanation remains within known physics. The challenge is to decide whether light is pushing the object's mass or merely pushing its dust, and therefore pushing the measured centroid. The decision depends on the quality of imaging, on the stability of residual patterns across measurement methods, and on whether the inferred acceleration implies an area-to-mass ratio that is compatible with plausible physical properties of a small solar system body. Deeper inward, the focus shifts from direct light pressure to the quieter influence of heat itself. When sunlight warms a rotating body, the surface absorbs energy and later re-emits it as infrared radiation. Emitted radiation carries momentum, and because emission is not always perfectly symmetric, a net recoil force can result. This is the core of thermal recoil effects. The best-known form for small bodies is the Yarkovsky effect, in which a rotating body experiences a tiny acceleration because the warmest region of its surface is typically shifted from the point directly facing the sun. The shift arises because the surface does not heat and cool instantly. Thermal inertia, the tendency of a material to resist temperature change, causes a lag. The afternoon side of a rotating body can be warmer than the morning side. As that warmer region radiates more strongly, the recoil pushes the body slightly. Over long times, this can measurably change the orbit of small asteroids. For certain sizes, it can be an important factor in delivering asteroids from the main belt into Earth-crossing orbits. Thermal recoil depends on size and on rotation. If the body is very large, the acceleration is very small, because mass is large relative to surface area. If the body is very small, it can heat and cool, quickly reducing the thermal lag. And it can also be influenced strongly by other forces like radiation pressure. There is an intermediate size regime where Yarkovsky can be most significant. The direction of the effect depends on the sense of rotation and on the orientation of the spin axis. For a body rotating in the same direction as its orbit, the thermal emission pattern can produce a thrust that either speeds it up along its orbit or slows it down, depending on whether the spin axis points above or below the orbital plane and on how sunlight strikes the surface across the season. The result can be a drift in semi-major axis over time, subtle but real. On shorter timescales, thermal recoil can produce small along-track deviations that might appear in residuals if the astrometry is precise enough and the arc long enough. The Yarkovsky family is broader than one simple picture. There are diurnal and seasonal components. The diurnal component arises from day-night heating and the afternoon thermal lag. The seasonal component arises when the spin axis is tilted, causing one hemisphere to experience a longer season of sunlight and warming, and then a longer season of cooling. The seasonal pattern can cause recoil in directions that differ from the diurnal effect. The relative strength depends on rotation period thermal inertia and spin axis orientation. In addition, the surface is rarely uniform. Boulders, regolith, and dust layers have different thermal properties. A patchwork surface can produce complex emission patterns that change as the body rotates. A related effect occurs when heat is conducted into the subsurface and then released with a delay. For porous materials, sunlight can penetrate into the top layer and warm it below the immediate surface. The delayed emission can shift the recoil direction. If the object is a cometary nucleus with active sublimation, thermal effects can interact with outgassing. Sublimation itself consumes heat-cooling active regions, while dust layers can insulate and create hotspots elsewhere. These interactions can change both the outgassing thrust and the thermal recoil, and they can shift as the surface evolves. This complexity makes it challenging to model thermal recoil precisely for a specific object, unless detailed physical properties are known. Thermal recoil also includes effects related to changes in rotation. Sunlight can exert torque on an irregularly shaped body because radiation pressure does not act through the center of mass uniformly when the shape is uneven and the reflectivity varies. The resulting torque can change the rotation rate and spin axis orientation over time. As the spin state changes, Yarkovsky acceleration changes because the direction of the thermal lag relative to the sun changes. This introduces a coupling, a small torque, changes rotation, and changed rotation changes the thermal recoil. For objects that tumble, the average recoil can shift unpredictably. Tumbling means the rotation is not about a single stable axis. Instead, the object's orientation changes in a complex way. In such cases, a simple Yarkovsky model may be inadequate, and the inferred acceleration may not align neatly with expected directions. To evaluate thermal recoil as a candidate for trajectory anomalies, analysts look for specific signatures. One signature is a slow drift in residuals that remains even when outgassing is unlikely and when radiation pressure alone cannot account for the direction or magnitude. Another signature is consistency over time, because thermal recoil is usually continuous and smooth, not episodic, unless the rotation state changes abruptly. The effect also depends on distance from the sun, but not in the same way as sublimation. Thermal emission scales with absorbed solar energy, but the thermal lag and recoil direction depend on material properties and rotation. This can produce distance dependence that is smoother and less steep than that of strong, volatile sublimation. If residuals show a gentle, consistent drift over months with little evidence of activity, thermal recoil becomes more plausible. Yet uncertainty remains because the physical inputs are often unknown. Thermal inertia is rarely measured directly for a newly discovered small body. It can sometimes be inferred from infrared observations, but those require favorable conditions and sensitive instruments. Rotation state can be inferred from light curves if the object is bright enough and the observational cadence sufficient. Light curves show periodic brightness variations as the object rotates. A stable period suggests a stable spin. A complex or changing pattern suggests tumbling. Even with a light curve, the spin axis orientation is hard to determine without extensive data. Surface roughness and albedo reflectivity also affect heating. An object with a dark surface absorbs more sunlight and heats more, increasing thermal emission and potentially increasing recoil magnitude. But albedo is also hard to infer without size information, In many cases, thermal recoil is not the dominant explanation for a dramatic seeming claim because its magnitude is typically small over short spans. But small does not mean irrelevant. If the anomaly is subtle and measured at high precision, thermal recoil can matter. The challenge is to avoid treating it as a convenient catch-all. In careful practice, analysts test whether plausible combinations of size density rotation and thermal inertia could produce the inferred acceleration. If the required parameters are extreme, thermal recoil becomes less likely. If the required parameters fall within known ranges for similar objects, it becomes more likely even if not proven. Thermal recoil can also interact with surface evolution. As a body approaches the sun's surface, temperatures can change enough to cause cracking, devolatilization, or dust movement. Dust can migrate to cooler regions, changing local thermal properties. A new dust layer can insulate underlying material, increasing thermal lag. An exposed rocky patch can increase thermal conduction. These changes can shift Yarkovsky magnitude and direction over time. For an object on a first close approach, after long cold storage, surface evolution can be rapid on a relative scale, though still subtle. Such changes could lead to a slow drift that is not perfectly constant. In the context of an object whose trajectory is said to be altered beyond explanation, thermal recoil serves as a reminder that physics includes mechanisms that are gentle and cumulative. A small mismatch between a gravity-only orbit and observations does not require new laws. It can arise from the steady push of infrared photons emitted a little out of balance, guided by rotation and material response. Yet thermal recoil is also a mechanism that demands humility because it is hard to quantify without more data. It can be evaluated as plausible, constrained by reasonable physical parameters, and tested against observations that reveal size, rotation, and thermal properties. As the analysis moves inward, thermal recoil stands between the more visible activity-driven thrust and the deeper complications of shape and spin, linking the object's physical character to its dynamical behavior through the quiet exchange of heat and momentum. The inward path now reaches the object's rotation state and shape, because many small forces depend not only on how much energy arrives from the sun, but on how that energy is distributed across an irregular body as it turns. A perfectly spherical object with uniform surface properties tends to average forces symmetrically. Real small bodies are rarely like that. They are lumpy, elongated, sometimes bilobed, sometimes covered in boulders and dust, sometimes fractured and porous. Their spin can be stable, slow, fast, or chaotic. This physical complexity does not merely decorate the object. It changes how forces act and how those forces project into measurable deviations in the trajectory. Rotation state is often inferred from photometric light curves. As the object rotates, its projected area and surface brightness pattern change, causing the observed brightness to vary periodically. A simple repeating pattern suggests a principal axis rotation, meaning the object spins around a stable axis. A more complex pattern with multiple periods or irregularities suggests non-principal axis rotation, commonly called tumbling. Tumbling means the object's orientation evolves in a more complicated way, and the relationship between the sun direction and surface features changes from one rotation to the next. For force modeling, tumbling is a challenge because it can average or randomize certain effects. A jet that points in a particular body-fixed direction will not always point the same way in space if the body's spin is unstable. Thermal recoil depends on where the warmest region is relative to the sun and to the spin and tumbling changes that continuously. Shape is coupled to rotation through inertia. An elongated object has different moments of inertia along different axes. Collisions outgassing jets or radiation torques can shift it into tumbling if the rotational energy is distributed among axes. Over time, internal friction can damp tumbling back into a stable rotation, but the damping timescale can be long for small, rigid bodies and can be shorter for rubble piles with internal movement. The physical structure matters. A rubble pile is a gravitational aggregate of rocks and dust held together loosely. Such bodies can dissipate energy through internal rearrangements. A monolithic fragment can behave more rigidly. In a newly discovered object, structure is usually unknown. Yet structure influences how easily spin changes and how stable a modeled force direction can be. Irregular shape also changes how sunlight is absorbed and emitted. Concavities create self-shadowing. Rough surfaces present facets at many orientations. A facet facing the sun heats while a neighboring facet in shadow remains cooler. As the object rotates, the pattern of heating can shift abruptly when a facet moves into sunlight. This can change thermal emission anisotropy and therefore thermal recoil. If the body has a high thermal inertia, these changes are smoothed by slow heating and cooling. If thermal inertia is low, the surface responds quickly, producing a more immediate relation between illumination and emission. Either way, irregular shape increases the complexity of the net recoil force. A simple model that assumes a smooth temperature distribution may fail to capture the true behavior. Shape also influences outgassing if volatile patches exist. Gas escapes more readily from regions with fractures, cliffs, or porous vents. An irregular body can channel gas into collimated jets. If a jet emerges from a specific area, its direction in the body frame is fixed, but its direction in space depends on rotation. For a stable rotation, the jet sweeps out a cone in space, and the time average thrust depends on how the jet is illuminated and on how the rotation axis is oriented relative to the sun. For tumbling, the jet direction in space can wander, potentially reducing net thrust or producing variable thrust. This can create residual patterns that vary over time. It can also make a standard non-gravitational model with fixed components inadequate. Another inward complication is the way rotation can change due to torques. Radiation pressure can exert torque on an irregular body when the distribution of reflected and emitted photons is asymmetric. Outgassing jets can exert torque as gas leaves the surface, often with a lever arm relative to the center of mass. These torques can spin the object up or down and can tilt its spin axis. Over time, a change in spin axis orientation changes which regions receive more sunlight, which changes outgassing patterns, which changes thrust. The system becomes a feedback loop. In some cases, spin up can lead to mass shedding if centrifugal forces overcome local cohesion. Mass shedding can release dust and change brightness. It can also alter the object's shape, changing the torque environment. Such processes are complex, but remain within known mechanics of rotating bodies. Rotation complicates trajectory modeling because force direction in inertial space depends on orientation. A purely gravitational orbit model does not need orientation. A non-gravitational model often assumes that the extra acceleration aligns with certain orbital frame directions and scales smoothly with solar distance. This is an approximation that works well for many comets, because the net effect of many jets and rotation averages into a relatively stable pattern. For an object with unusual rotation, or with a single dominant active region, the approximation can fail. The residuals may show changes in direction that a simple model cannot capture. Analysts then must decide whether to add more parameters, which risks overfitting, or whether to seek additional physical constraints, such as rotation period and axis orientation, to guide a more realistic model. The object's shape also affects how its position is measured. If the object is unresolved, shape does not directly affect astrometry, but it affects brightness and therefore signal to noise. If the object is slightly resolved or trailed, shape can influence the light distribution, shifting the centroid. For an active object with dust, shape influences the coma distribution, because dust may be emitted preferentially from certain regions. The center of light can then move in a way tied to rotation. This can introduce periodic patterns in astrometric residuals. If residuals show periodicity matching the rotation period inferred from photometry, it suggests that the measured position is being modulated by rotating asymmetries rather than by a steady acceleration. Such a finding would shift attention back toward measurement bias and coma modeling, even if outgassing thrust is also present. To make progress in this region, analysts link different data types. They compare light curve-derived rotation states with residual time series. They look for changes in brightness that coincide with changes in residual patterns. They examine imaging for jets or asymmetric coma features that rotate or change with time. They assess whether the inferred acceleration direction changes in a way consistent with a changing spin axis. If the object is bright enough, radar observations or direct imaging can reveal shape, but such opportunities are limited and depend on distance and geometry. More often, shape is inferred indirectly and uncertainty remains. What emerges is that physics can explain many apparent oddities, but only if the object's physical state is considered. A phrase like altered trajectory can hide the fact that a small body is not a point mass. It is a rotating, irregular, evolving object interacting with sunlight. A tiny thrust or recoil that depends on orientation can produce residuals that look puzzling when modeled as a simple function of distance alone. When rotation is stable and activity is distributed, the averaging works and models are simple. When rotation is complex and activity localized, the averaging fails and models must be more nuanced. This inward region does not resolve the motion by itself, but it changes what it means to say a model fails. The failure may not be a failure of physical law. It may be a failure to incorporate orientation-dependent forces because the orientation is unknown. It may be a failure to separate nucleus motion from centroid motion because the coma is asymmetric. It may be a failure to capture time-variable thrust because jets turn on and off as the object rotates. Understanding these possibilities requires keeping the physical body in view, not just the orbit. In that sense, the trajectory is not only a path through space, it is a record of how an irregular spinning object exchanges momentum with light and gas as it moves, and how that exchange is filtered through measurement methods that see brightness before they see mass. Before concluding that a small body's residuals require unfamiliar forces, the next inward layer checks whether ordinary gravity might still be missing something. The baseline includes the Sun and planets, but the solar system is not empty between them. Many smaller masses exist, and certain configurations can produce perturbations that are small yet measurable. The first question is whether any close encounter has occurred or is occurring. A close encounter means the object passes near a planet, a large moon, or another massive body closely enough that the gravitational tug noticeably bends the trajectory. Such an encounter can produce a change that looks like a deflection, but it is fully predictable if the encounter is known and modeled. The difficulty is that a close encounter can be overlooked if the preliminary orbit is uncertain or if the object's path brings it near a body that is not included in a simplified model. In the inner solar system, the major planets are well tracked, and their masses are known to high precision. Their perturbations are typically included automatically. Yet some gravitational effects can still slip through if the model is not configured for the required precision. For example, the influence of large asteroids can matter for precise orbit work in certain regions. The most massive asteroids are concentrated in the main belt. For an object passing through or near that region, neglecting their combined influence could create small residuals over long arcs. The influence of a single large asteroid is generally much smaller than that of a planet, but when measurement precision is high, small terms can become relevant. Analysts test this by adding additional bodies to the integration and seeing whether residual patterns change. If the anomaly disappears when additional known masses are included, the explanation returns to gravity not because gravity is new, but because the baseline was incomplete. Hidden perturbers are also considered more broadly. The term does not imply mystery bodies. It implies the possibility of an unmodeled gravitational influence from an object whose existence is known, but whose role in the specific calculation was omitted, or from a small body whose ephemeris is uncertain. In practice, the strongest candidates are known planets and the largest asteroids. In rare cases, a close pass near a small body, even a relatively small one, could produce a brief perturbation if the pass is extremely close. Such events are unlikely because the volume of space is large, but not impossible. The challenge is that proving such a close encounter requires accurate trajectories for both bodies and a confirmed close approach distance. Without that, it remains a low probability hypothesis. Another gravitational complication comes from the observer's frame. If the calculation uses an Earth-centered approach, or if it converts between frames, incorrectly apparent residuals can arise. This is not a hidden perturber in space, but it is a hidden perturbation in computation. In careful work, analysts compare results from independent orbit determination software and independent ephemerids. If different teams using different software find the same residual pattern, it reduces the chance that the anomaly is a computational artifact. If the pattern is sensitive to software choices, it suggests an implementation issue rather than new physics. Gravitational perturbations also include effects of non-spherical mass distributions of planets during very close approaches. For example, the gravitational field near a planet is influenced by the planet's oblateness, its equatorial bulge. For most asteroid or comet flybys at typical distances, The effect is small compared with the overall planetary gravity term. But for very close flybys, including such terms can matter. Similarly, close passes near a large moon can produce a measurable effect if the object passes within the moon's sphere of influence. These are rare, but must be checked if geometry allows. The baseline gravitational model often includes these effects only when needed. So part of the inward work is to determine whether the specific case demands them. In addition to known masses, analysts consider whether the object might be a binary or a fragmenting system. If the object is actually two bodies orbiting each other, the center of light may shift as their mutual configuration changes. This can introduce periodic astrometric residuals that could be mistaken for a trajectory anomaly. The effect is typically small unless the binary is wide or the components have different brightness. Detecting binarity requires high-resolution imaging mutual event photometry or unusual light curve signatures. Fragmentation, where a body breaks into pieces, can also alter the observed centroid. If one fragment becomes dominant in brightness, the measured position can shift. Fragmentation can be accompanied by increased brightness and a changing coma. This again highlights that what is tracked is often the brightest component, not necessarily the original center of mass. A different gravitational aspect is whether the object's orbit brings it through regions where solar tides and planetary tides interact in subtle ways. Tides are differential gravitational forces that stretch objects. Tides affect the object's internal stress and can contribute to fragmentation or surface changes, which can in turn affect outgassing and dust release. The tidal force does not directly accelerate the center of mass in a way that changes the orbit, because the center of mass motion still follows gravitational dynamics. But tides can cause physical changes that lead to non-gravitational forces. In that sense, gravity can be the upstream cause of an apparent non-gravitational anomaly through physical evolution. This pathway remains within physics, but involves a chain of effects rather than a direct tug. The inward check for gravitational completeness also includes the possibility of an encounter with a ring system or dust environment around a planet. Passing through a diffuse ring could produce drag forces or collisions with particles, potentially altering the object's motion or its activity. However, this is highly dependent on the object's path and is usually relevant only near the giant planets. For a typical inner solar system object, such interactions are unlikely. Still, the principle remains: if the orbit passes near a complex environment, the environment must be considered. When all plausible gravitational contributions are included, and when no close encounters or omitted masses can account for the residuals, the analysis can move forward with greater confidence that the deviation is truly non-gravitational. Yet even then, the phrase physics cannot explain; it is still too broad. The residuals may resist simple models, but resistance can arise because the object's non-gravitational forces are time variable or orientation dependent, not because forces are unknown in principle. The gravitational check serves as a gate. It ensures that the simplest and most reliable class of forces, gravity, is not being undercounted. It also clarifies that a sudden apparent change in trajectory is often the signature of a close encounter, which is dramatic but explainable. This region therefore narrows the mystery by removing a set of possibilities. If a close encounter exists, the altered trajectory has a gravitational cause and should be predictable. If a missing mass term explains the residuals, the baseline is corrected and the anomaly dissolves. If computational frame errors are found, the anomaly was in the arithmetic rather than in the sky. If binarity or fragmentation explains centroid shifts, the anomaly is observational rather than dynamical. If none of these fits, then the remaining residuals point back inward to the subtle forces already discussed and to the possibility that their combination and time dependence is not yet captured by standard parameterizations. The object remains within a web of known influences, but it demands a careful accounting of which strands have already been measured and which remain only loosely constrained. When gravity is accounted for and the measurement chain is audited, yet residuals still persist. The language used by careful analysts becomes the final safeguard against turning an unresolved fit into a claim that laws have failed. In this region, the focus is not on adding new forces immediately, but on how uncertainty and model limitation are described. A model can fail in many ways that do not imply the underlying physics is broken. It can fail because it is oversimplified. It can fail because key physical properties of the object are unknown. It can fail because the data set is still incomplete in geometry or quality. It can fail because different effects overlap and the data cannot uniquely separate them. The phrase "cannot explain" is therefore examined as a statement about the current state of modeling and evidence, not as a statement about nature's impossibility. One form of model limitation is parameter degeneracy. This occurs when different combinations of forces produce similar residual patterns over the available time span. For example, a weak outgassing thrust in a certain direction can mimic the effect of a small centroid bias from a dust coma that is asymmetric in the same direction. Radiation pressure on a low-mass object can mimic a radial outgassing component if the direction is roughly anti-sunward. Thermal recoil can mimic a transverse thrust if the spin axis orientation is such that emission produces a long-track acceleration. Over a short arc, these effects can be hard to separate. Even over a longer arc, separation may require additional data types, such as resolved imaging spectroscopy or thermal infrared measurements. If those data are missing, the orbit fit may be improved by multiple competing models. In that case, saying physics cannot explain is not accurate. The honest statement is that the current data do not uniquely discriminate among plausible physical mechanisms. Another limitation is the temporal variability of forces. Many standard non-gravitational models assume smooth dependence on distance from the Sun. This works reasonably well for many comets, because sublimation-driven thrust often varies smoothly with solar heating, at least in a coarse averaged sense. But an object can behave in more complex ways. Activity can turn on and off as the object rotates, producing modulation. A localized jet can dominate, producing thrust that changes direction with spin. An outburst can produce a temporary spike. A fragmenting body can change its shape and active surface area. Even if each of these behaviors is physically ordinary, the combined effect can produce residuals that appear irregular. A smooth model can then underfit the data, leaving structured residuals. The right conclusion is not that physics is broken. The right conclusion is that the object's force history is more complex than the model's parameterization. A third limitation is the fidelity of the astrometric target. The orbit integration follows the center of mass. The observations often follow the center of light. If the center of light shifts with coma changes, the astrometry includes a time variable bias. In principle, this can be corrected by modeling the coma and locating the nucleus. In practice, the necessary imaging resolution and signal-to-noise may be lacking. If the object is faint, the nucleus may be buried within the coma. If the coma is asymmetric, different observers using different apertures and algorithms can produce slightly different positions. The result is that the data set itself is heterogeneous. This heterogeneity can create residual patterns that no dynamical model can fully remove, because the underlying measurements do not represent a single physical point consistently. In such a situation, saying physics cannot explain it mistakes a measurement limitation for a dynamical mystery. Careful analysts therefore rank hypotheses by how well they are supported and how many assumptions they require. They also track how the fit behaves under prediction. A model that fits past data but fails to predict future positions is not a good explanation. A model that improves prediction is stronger. Prediction is the crucial test because it reduces the risk of overfitting. When a non-gravitational term is introduced, it must not only reduce residuals for existing data, it must also provide better forward predictions. If it does, the term likely captures a real aspect of the motion, even if the physical cause behind the term is still debated. If it does not, the term may be compensating for noise or biases. In this region, the phrase "physics cannot explain" is replaced by more precise statements. One might say that a gravity-only model leaves statistically significant residuals. One might say that a standard cometary non-gravitational law does not fully account for the deviations. One might say that the inferred acceleration changes direction over time in a way that suggests variable activity or rotation. One might say that the data are consistent with more than one physical mechanism, and that additional observations are required to distinguish them. Each of these statements has a different meaning and different implications. None requires new physics. Each points to a next measurement. Another important practice is to quantify significance without overstating it. Significance depends on realistic uncertainty. If uncertainties are underestimated, residuals appear more significant than they are. If uncertainties are inflated, real signals can be hidden. Analysts therefore examine the distribution of residuals, adjust weights to reflect correlated errors, and sometimes use robust statistical methods that are less sensitive to outliers. They also compare results from independent teams. If an anomaly appears in one pipeline, but not another, it may be a reduction artifact. If it appears across pipelines, it is more likely real. This cross-comparison is part of scientific caution. It recognizes that orbit determination involves many choices, and that agreement among independent implementations is a form of validation. The phrase "cannot explain" also implies finality, but orbit analysis is often iterative. As new observations arrive, the anomaly can shrink or change character. A deviation that seemed dramatic on a short arc can disappear as the orbit becomes better constrained. Conversely, a subtle drift can become clearer. An object can also change behavior. Activity can decline, causing non-gravitational terms to weaken. A coma can dissipate, making astrometry cleaner. In such evolving conditions, any statement about what physics can or cannot explain must be tied to a specific time window and a specific data set. Otherwise, the statement floats free of context. In this region, The analysis also recognizes the human tendency to interpret residuals as mysteries. Residuals are compelling because they are the difference between expectation and observation. Yet differences are common in science, and most are resolved by improving models or measurements. The disciplined posture is to treat residuals as clues rather than as contradictions. A residual pattern may indicate outgassing. It may indicate radiation pressure. It may indicate thermal recoil. It may indicate centroid bias. It may indicate a combination. Each candidate has testable consequences. Outgassing should correlate with activity indicators. Radiation pressure should imply a plausible area to mass ratio and should act away from the sun. Thermal recoil should relate to rotation and thermal properties. Centroid bias should depend on aperture and imaging morphology. The correct response is to design observations that can test these consequences. As this inward region concludes, the apparent boundary between explainable and unexplainable is reframed. The boundary is not between physics and non-physics. It is between what is constrained and what is not yet constrained. Physics provides many mechanisms that can produce small accelerations. The challenge is to determine which mechanism applies in a particular case with the available data. If the data are insufficient, the honest outcome is uncertainty. Uncertainty is not failure. It is the state that motivates further measurement. Thus, when a trajectory is said to be altered and not explained, the most careful interpretation is that the current models and measurements do not yet fully account for the observed residuals within realistic uncertainties. The next step is not to abandon physics. It is to tighten constraints by extending the arc, improving imaging measuring spectra, refining rotation state, and testing model predictions against new observations. The inward path reaches its most concrete level when it asks what the object is physically and what tests can be applied next. Because explanation in this context is not a single sentence. It is a set of constraints that narrow until only a few mechanisms remain. The object is first treated as a body with mass, surface temperature response, and potential volatiles. Even without direct sampling, certain properties can be bounded. The brightness and its variation over time provide clues about size, shape, and rotation. The presence or absence of a coma, even a weak one, provides clues about activity. Spectral measurements, if obtained, provide clues about composition, or at least about the presence of gas species. Thermal infrared observations, if available, provide clues about size and albedo by separating reflected sunlight from emitted heat. Radar observations, if geometry allows, provide direct constraints on size, shape, and rotation. Each constraint is a step inward, turning a generic small body into a specific object with a narrower range of plausible behaviors. A practical physical picture begins by separating nucleus-dominated light from coma-dominated light. If imaging shows the object remains point-like under high resolution and high signal-to-noise conditions, the nucleus likely dominates, and centroid bias from dust is reduced. If imaging shows extended structure, then the measured position is potentially affected by that structure. In such cases, one test is to measure positions using different apertures or fitting methods. If the measured position shifts when the aperture changes, extended, light is influencing the centroid. This indicates that a portion of the residual pattern may be observational rather than dynamical. Another test is to attempt nucleus extraction by fitting the inner coma profile and subtracting a point spread function, allowing a better estimate of the nucleus location. If such methods reduce residuals, they point towards centroid bias as a major contributor. If the object shows signs of activity, the next physical question is which volatile could be driving it at the observed distance from the Sun. Activity far from the Sun suggests more volatile substances than water, while activity closer in can be driven by water ice. Spectroscopy can search for gas emission features or for continuum slopes consistent with dust. Even when gas lines are not detected, upper limits can be set constraining how much gas is produced. These constraints can be compared with the acceleration inferred from orbit fitting. If the required gas production to produce the measured thrust is far above the observed limits, then outgassing thrust becomes less likely, as the main driver, or the thrust, must be produced by a different mechanism such as directional emission from a small active area that is hard to detect spectroscopically. If the required production is compatible with limits and the object shows coma behavior, outgassing becomes more plausible. If activity is weak or absent, radiation pressure and thermal recoil move higher in priority. To evaluate radiation pressure, the key physical quantity is the area-to-mass ratio. Thermal infrared observations can help estimate size by measuring heat emission. If size is constrained, and if density can be bounded by plausible ranges for rock or porous material, mass can be estimated. With size and mass in hand, area-to-mass ratio can be computed, and the expected radiation pressure acceleration can be compared with the inferred acceleration. If the inferred acceleration requires an implausibly low density or an implausibly thin structure, radiation pressure becomes less likely. If the required parameters are plausible, radiation pressure remains in play. Similarly, to evaluate thermal recoil, constraints on rotation period and spin axis orientation are helpful. Light curves provide period. Longer campaigns with varying viewing geometries can provide hints about spin axis. Thermal inertia can be constrained by infrared measurements at different phase angles or times. If the inferred acceleration aligns with a plausible Yarkovsky scenario given rotation and thermal properties, thermal recoil becomes a viable explanation. Rotation itself can be tested more deeply. High-cadence photometry over many nights can reveal whether the rotation period is stable or whether the object tumbles. If the period changes over time, a torque is acting potentially from outgassing or radiation. If tumbling is present, models that assume steady thrust direction become less reliable and residual variability may be expected. A tumbling state can also be inferred from changes in the light curve shape that cannot be explained by changing viewing geometry alone. Such findings would suggest that non-gravitational forces may be complex and time variable, yet still rooted in known processes. Another physical test is to look for correlations between residuals and activity indicators. If residual drift increases as brightness increases and imaging shows coma growth, then activity-related explanations become stronger. If residuals persist while brightness is stable and the object remains point-like, then activity-related centroid bias becomes weaker and direct dynamical effects like thermal recoil become relatively stronger candidates. Correlation tests can also be performed with solar phase angle. If brightness changes coincide with phase angle changes without corresponding changes in residual behavior, geometric scattering may be responsible for brightness variation rather than changes in thrust. Continued tracking is itself a powerful test. Many non-gravitational forces have distinct time dependence. Outgassing often peaks near perihelion and can show asymmetry before and after perihelion because of thermal lag. Radiation pressure varies smoothly with solar distance and remains directed away from the sun. Thermal recoil depends on rotation and can persist even when activity fades, though its magnitude can change as distance changes. If the object is followed long enough to observe how residuals evolve with solar distance and geometry, the signature can become clearer. A model that includes a fitted acceleration can be tested by its ability to predict positions weeks ahead. If it consistently improves predictions, it captures real physics, even if the exact mechanism remains uncertain. If it fails, the fit may have been compensating for biases or transient behavior. There is also the possibility that the object changes physically, which alters the force environment. An outburst can change surface properties and activity. A fragmentation event can change the mass distribution and create multiple sources of light. A mass shedding episode can create a dust cloud that dominates brightness and biases astrometry. These events are tested by monitoring morphology and by searching for sudden photometric changes. If such events occur, the dynamical modeling must account for time-variable forces and for possible shifts in what is being tracked. In such cases, it becomes crucial to define whether the measured positions refer to the same physical component over time. At this innermost point, the phrase "physics cannot explain" it becomes least accurate and least useful. The more productive statement is that the current data constrain the object to behave in one of a set of physically plausible ways, and that the remaining uncertainty lies in specific parameters that can be measured. The next tests are therefore concrete. Obtain deeper imaging to separate nucleus from coma. Obtain spectra to search for gas and constrain production. Obtain light curves to characterize rotation and possible tumbling. Obtain thermal observations to estimate size and albedo. Extend the astrometric arc to test whether a fitted acceleration improves prediction over time. Compare independent reductions and independent orbit fits to ensure robustness. Each test moves from broad assertion toward measurable constraint. In this way, the object's trajectory is not merely a curve that needs explaining. It becomes a probe of surface physics, thermal response, and activity. The explanation is not a single mechanism chosen by preference. It is the intersection of dynamical evidence and physical observation. When that intersection is narrow enough, the anomaly stops being a headline and becomes a quantified acceleration tied to a plausible physical cause. Even if uncertainty remains, the uncertainty can be stated precisely as a range of accelerations, a range of sizes, a range of possible thrust mechanisms. The inward journey ends with this clarity motion that appears puzzling at first, often becomes ordinary when the object is described not as a point moving through space, but as a physical body interacting with sunlight heat and its own evolving surface. And when each component of that interaction is tested with observations designed to reduce ambiguity rather than to amplify surprise. As the observations continue, the object remains a small moving point, that becomes a set of constraints rather than a riddle. The sky provides angles, times brightness, and shape in the image, and each of those measurements is filtered through instruments, catalogs, atmosphere, and reduction choices. When the orbit is stable enough that new points no longer move the solution in large jumps, any remaining drift between prediction and measurement becomes a measured signal with a size, a direction, and a dependence on time. That signal may belong to the object's motion, or it may belong to the way the object's light is distributed, and the difference matters. If the residual pattern tracks brightness and coma growth, the measurements likely carry the imprint of dust and gas, and the center of light may not sit on the center of mass. If the residuals persist when the object looks point-like and stable, the emphasis shifts toward forces that act on the body itself, such as weak outgassing from a small patch radiation pressure on an unusually high area-to-mass body, or thermal recoil shaped by rotation and surface properties. The phrase that physics cannot explain is replaced by a more careful posture. The current model set does not yet fit the current data within realistic uncertainty, and the missing piece may be a known mechanism whose parameters are not yet measured. Each candidate mechanism suggests a practical test. Deeper imaging can reveal whether a coma exists and whether its asymmetry could bias astrometry. Spectra can detect or constrain gas that would support outgassing thrust. Light curves can reveal stable rotation or tumbling that would complicate force direction. Thermal measurements can constrain size and albedo, tightening mass estimates and the plausibility of radiation pressure or thermal recoil. Continued astrometry can test prediction, the strictest measure of whether an added acceleration term represents a real effect. In this steady, layered approach, surprise gives way to accounting. The object's path becomes a record of small forces acting over time, and the limits of explanation become specific rather than absolute. The work continues until residuals either dissolve into the known imperfections of measurement or remain as a quantified acceleration that points to a constrained physical cause. Either outcome is a form of clarity reached by moving patiently inward from the sky's first detection to the object's physical character, one tested layer at a time.